Thank you, Ben. So I'm going to present to you today some of my work from my PhD over the last few years. The work is in three parts: laboratory investigations, in situ monitoring, and then some theoretical modelling to work towards regulation. The first section, measuring emissions from cooking in laboratory tests. This was work that I conducted alongside TNO to investigate emissions from cooking full meals, factors affecting these emissions, and the potential reduction of using a typical cooker hood, as cooking is a key source of PM2.5 indoors, and we wanted to investigate the effect of cooking multiple components at the same time, as that hadn't previously been studied in detail. As this work involved measuring emissions from 4 different meals. The first was fried chicken, fried potatoes, and boiled green beans. Second was fried chicken, boiled potatoes, and boiled green beans. Third was the pasta bolognese, and the fourth was a chicken and vegetable stir fry. These were supposed to be somewhat representative of European cooking styles. So here we can see some of the results. On the left is plots of concentration over time measured during cooking the meals, and we can see that the emission characteristics vary during cooking and between meals. There wasn't constant emissions throughout the cooking period for any given meal, and the profiles are very different between the different meals. Meal 1 and meal 2 are fairly similar. However, meal 3, the pasta bolognese, and meal 4 are distinctly different. Meal 3 had a much higher initial peak, which then emissions slowed down fairly early on in the cooking process once the liquid was added. And meal 4 had a double peak, which coincided with the high temperature frying of the meat and then the vegetables. As you can see, the emission rates shown on the right were also very different between the meals. More information can be found in the paper, this work has recently published in Indoor Air, and the reference is on the screen. The second section of this is in situ measuring, which was a simple intervention study to investigate what PM2.5 concentrations are found in student kitchens, and can these concentrations be reduced by encouraging occupants to use existing methods of ventilation. So here's an example test setup. We've measured in student kitchens for 2 weeks using a side pack to monitor PM2.5 concentrations and an IAQ calc to monitor other parameters. Both devices are measured are located away from the stove and other pollutant and heat sources, with the aim being to measure mixed air within the kitchen. All the households included are non-smoking households. During the first week, we asked the occupants to record their cooking activity to check how that lines up with PM2.5 concentrations measured. And then after the first week, we show them the data from the first week, give some indication on the health impacts of exposure to high concentrations of PM2.5, and then some suggestions of how they could use different ventilation methods to try and reduce the concentrations in the second week. And in the second week, we also ask occupants to record ventilation use, particularly during cooking. Of the houses I'm talking about today, all of these were fitted with cooker hoods, which do extract to outside, although the one in house A was damaged, so some of the air may have been recirculated. So here we can see on the left concentrations measured over time in one of the houses for 1 week. and on the right is the distribution of concentrations from week 1 to week 2 in each house in turn. Whilst I have also overlaid the WHO daily mean threshold of 25 micrograms per meter cubed for PM2.5. However, this comparison is somewhat problematic, as the side pack is an optical device which measures based on the particles like scattering effect on a laser, and should also have concurrent gravimetric sampling, which we didn't have. So the device may have overestimated or potentially underestimated the concentrations measured during this period. What is more interesting, however, is that on the left in orange, I've highlighted the concentrations measured during recorded cooking periods. The concentration is generally higher during these periods, which is what we would have expected to find, and confirms that cooking seems to elevate concentrations. Not all the peaks are captured in the recorded cooking periods. There are many potential reasons for this, such as errors in recording the times for cooking or the time it takes for emitted pollutants to mix in the air. What's more important is that only 2 of the houses show a decrease in concentrations during the second week. That would be House C and House D. All the others show a statistically significant increase, which is the opposite effect of what we wanted to find. Although there are many reasons that this could have occurred that aren't to do with the intervention, we measured 2 separate weeks of cooking, of normal behaviour for student households where cooking behaviour can be highly cooking and living behaviour can be highly variable. So it may be differences in the way the occupants were using the space in general. And so onto my third section. This is ongoing work to predict internal concentrations in UK kitchens and test the existing building regulations using a tried and tested modelling approach, augmented to assess uncertainty, and it also allows for a sensitivity analysis to test the relative importance of inputs. Here, the model is a fairly simple single-zone model, modelling just the kitchen in isolation from the rest of the dwelling. We assume perfect mixing in winter conditions, so no windows. There would be background ventilation from infiltration, and then either mechanical ventilation on top of that, either as general extract or through a cooker hood where there's also a capture efficiency. And with a single pollutant cooking source at different points during the day, as shown on the example cooking source function, where we have 3 emission periods during the day at variable spacing. So about some of the inputs, we consider 3 cooking periods per day. The first one of these is toasting, based on data we've collected, and this is a short duration meal, so short duration cooking period, so representative cooking breakfast. The other meals use emission rates from the full meals presented earlier with a longer duration. The spacing between the meals is highly variable to count for additional error due to lack of data on cooking behaviour in the UK. The kitchen volumes are taken from the English Housing Survey and infiltration data from Donbank. So we use this data to calculate the average concentration over the 24-hour period. The initial scenarios we consider are an infiltration only as a baseline, constant 13 litres per second mechanical extract, or which is a general extract, intermittent 60 litres per second using an extractor fan away from the stove, or 30 litres per second with a 50% capture efficiency, which is arbitrary. The flow rates for these are taken from the approved document F of the UK building regulations. The capture efficiency we've had to assume, as there's no mention of this in the existing regulations. We, for the intermittent flow conditions, we also consider two scenarios: just using it during cooking or continuing ventilation for an additional 10 minutes afterwards to test the potential benefits of this small behavioural change. And we compare the concentrations against the WHO PM2.5 daily mean threshold, which, as I've said before, is 25 micrograms per metre cubed. The method uses Monte Carlo methods so we sample from a distribution of data similar to the one seen on the screen. This allows for us to consider error and variability within all the inputs. So the initial predictions, as you can see, the infiltration, none of the scenarios perform particularly well compared to the WHO daily mean threshold, especially if we're not considering the additional 10 minutes of ventilation, as most houses, the daily mean concentration is considerably above that threshold. However, with the additional 10 minutes of ventilation, it makes a large difference, where for general extract, more than 50% of kitchens stay below the threshold using the cooker hood, and using the cooker hood almost 50%. So ventilating for an additional 10 minutes could be extremely useful and beneficial. Whilst it's useful to assess the existing regulations, it's more interesting and more beneficial to start setting what the flow rate should be. So here I've taken run the model for a range of flow rates. This is for a constant ventilation rate. The same method could be used for the intermittent, and by taking the point where in each line is for a different percentile, and by taking the point where they intersect with the WHO threshold, we could predict what ventilation rate should be used. So, for example, here we predict a ventilation rate of 40 litres per second for 75% of kitchens to remain below the threshold concentration. This is almost 4 times the 13 litres per second currently required. This is also equivalent to about 6 air changes per hour in constant ventilation. As I say, the same technique could be used for the intermittent ventilation. It's more complex when we start to consider capture efficiency as well with a cooker hood, because there's then a relationship between the capture efficiency and the flow rate. So here I've taken for different combinations of capture efficiency and for the flow rate of 30 litres per second. And for each capture efficiency, I found the percentage of kitchens below the average, and that's what's plotted. This could then be done with 20 litres per second, 40 litres per second, or indeed any combination of flow rate and capture efficiency. As a 3D plot, this looks pretty but isn't particularly helpful to use, but we can then effectively slice through it horizontally at different percentages of kitchens to get a relationship for the required combination of capture efficiency and flow rate to keep concentrations below a given threshold, such as this. So at lower capture efficiencies, where there's less pollutant captured at the source, leaving the fan on after cooking makes a huge difference to the flow rate needed. That's the dashed lines. This could also then be used in combination with data on the measured performance of existing cookers. So, for example, if I simplify it down, here's the 75% tile lines. So, with this example hood, using the ventilation just during cooking, we predict a flow rate of about 40 litres per second with a capture efficiency of 76%, which in 75% of kitchens would mean the concentration over 24 hours remained below the threshold. For the additional 10 minutes of ventilation, this reduces to about 30 litres per second, which is the same as the existing requirement with a capture efficiency of 64%. So this also gives incentives for cooker hood manufacturers to improve the capture efficiency of cooker hoods at lower ventilation rates, and further highlights the benefit of the additional 10 minutes of ventilation after cooking. Thank you.